Next, we are going to look at several memory allocation mechanisms. As we have mentioned in the previous slides, main memory must support both operating system and user processes. Due to the very limited memory resources, so we must deal with the memory allocation very efficiently. In the early stage, we have a relatively simple method which is called contiguous allocation. The idea is quite simple. We just divide the main memory into two partitions. The main memory just like a one-column table. On the top is the lowest memory address 0. The bottom is the highest memory address max. The operating system and the interrupt vector will be put on the top of the main memory space, which is started from address 0, and the user processes will be listed from the bottom. So each process contained in a single contiguous memory space, just like I have drawn the figure on the bottom of this slide. In this slide, we will learn how to use the following mechanism to achieve memory protection. In this mechanism, we use the relocation and the limit registers to protect user processes from each other and from changing operating system code and data. Here, relocation register contains the value of the smallest physical address that used to be assigned to this coming process. And the limit register contains the range that used to check whether the provided logical addresses are legitimate or not. If the logical address is less than the limit register, it means the logical address is valid. Otherwise, an addressing error will be triggered. And then we just use MMU to dynamically map the logical addresses to physical addresses. Down below, this figure illustrates how to implement the memory protection. So when CPU gives a logical address, it will be checked by the limit register to see whether it is legitimate. If yes, MMU will add this logical address with the relocation register to get a physical address and send this address to the main memory, then get the data or instructions we want. So here you need to be careful. Only using relocation register cannot guarantee the validation of the logical address. We have to combine with a limit register to check whether it is legitimate or not. And also, since here we only check the logical address instead of a physical address, only use a limit register will be good enough to tell whether the address is valid or not. For memory allocation, when a process arrives in the system, so we just allocate a memory partition from a hole that is large enough to accommodate it. So here we have a very important terminology, which is called hole. The hole represents a free memory block that can be allocated to a process. Down below, this figure shows us an example. During the whole procedure, so we just allocate the free memory block as a whole to different processes. And the new process arrive and the old process out. The size of a hole changed from time to time. So in actual memory, there may be numbers of holes with a various size. Then let's come back to the memory allocation mechanism. When a new process arrives the system, so we will allocate a hole that is large enough to accommodate it. After the process finishes the execution, so we will free the partition that previously assigned to it. If other free partition is adjacent to the newly released one, so we will combine them together to have a larger partition. To achieve this memory allocation mechanism, the operating system needs to maintain some additional information, such as the operating system needs to maintain the information about allocated partition, which means that the operating system needs to know which partition has been assigned to which process. And also, the operating system needs to know all the free partitions or holes so that when the new process arrives, the operating system can quickly assign a free partition to it. Then let's look at a problem that associates with the memory allocation mechanism, which is called the dynamic storage allocation problem. So when a new process with size n arrives to the system that requests a new partition, how to satisfy this request from a list of free holes? So actually, there are three mechanisms that can be used to achieve this goal. The first one is called first fit, which is the most simplest one. So we just sequentially search the list to find the first hole that is big enough to hold this process. And the second one is called best fit, which allocate the smallest hole that is big enough to hold the process. But this one may require to search the entire list unless the list is already ordered by size. And this one will produce the smallest leftover hole. For the leftover hole means we use the free hole to subtract the size of the process. And the remaining part of the free hole is called the leftover hole. And the last one is called worst fit. For this one, we will search the entire list to find the largest hole and assign it to the newly arrived process. So surely we can sort the list by size in descending order, and we just pick the top one and assign it to the new process. And this one will produce the largest leftover hole there. Then someone may ask that, why we need a worst fit? It looks like it does not provide a benefit to us. And also we can know it from the name that is a worst fit. So after we assign the largest hole to a process, we just waste a larger partition there. But actually the leftover hole can be reused by other processes. And also the larger leftover with a higher probability can be used by other processes compared to the smaller leftover hole, such as the one generated by the best fit. So let's look at an example to further illustrate it. And from the down below this figure. From this figure, you can see that the first fit and the best fit will generate a very small size of a leftover hole, which is hardly used by a typical process. On the other hand, the leftover hole generated by the worst fit can be used by other typical processes with a higher probability. However, the simulation results indicate that the first fit and the best fit are better than the worst fit in terms of speed and memory utilization.